Welcome back to science. Okay, we are continuing along with our history of the atom. At the end of the last lesson, I asked you to make your own timeline here and put the models in order. So I want to take a second to quickly review that. The first model is Democritus. And Democritus, ancient Greek, 2,400 years ago, believed that atoms were indivisible, and he thought of them as being like a hard marble. Early 1800s comes Dalton. He is considered the beginning of modern chemistry and modern atomic theory. It's almost 2,000 years later. It's over 2,000 years later. And he's still thinking that the atom is a hard marble, but he realizes that compounds are made of atoms, that elements are made up of different kinds of atoms. A little while later, Thomson comes along. He's the first one to realize the atom had charged particles in it. He's thinking about the atom like it's, he went to school, learned about Dalton with a hard marble, realizes that it's not a hard marble, it has charges in it. He thinks of it sort of like this jelly-like substance that has a positive charge, and the electrons are sort of embedded in there. So it's like, one of the analogies they use is chocolate chip cookie dough. The dough itself is like the positively charged gooey stuff, and then the chocolate chips would be like the electrons stuck in it. A little while later, Rutherford is working with Thomson's experiment, and he realizes that the protons, the positive charges, are not in this gooey substance. They're in a central nucleus, and the electrons are around the nucleus. So the model is getting more accurate to what we think. He's also the one that named the nucleus, came up with the idea that the atom had a nucleus. And a little while later is Bohr. And Bohr's model is very accurate to the way we think of the atom. He had a nucleus with protons and neutrons, and then he said the electrons were at different energy levels or orbitals around the nucleus. Now his model is, the only thing that's really wrong with it is flawed. So it's kind of like the solar system, the sun's here, and the Earth makes one circular rotation around the sun, and so do all the planets, okay? So it's not three-dimensional, but everything about it is an accurate representation. We know that there's a nucleus, we know that the electrons are at different energy levels, and they travel around the atom. The only thing is this one's not three-dimensional. So a little while later, people came up with the idea of the electron cloud. Instead of the atoms just going in a circle like this, they're kind of whirling all around in every direction on those energy levels, and that's why it looks like all these little spots are here, where you have the nucleus of the atom, and then all the positions the electrons could be around the nucleus. And then here's a reading that I shared with you, which briefly goes over the history of the atom. The important stuff here, Democritus. This is a review. He's the first person to suggest the idea of atoms. 2,400 years ago, Democritus asked whether it was possible to divide a sample of matter forever. And he came to the conclusion that it wasn't. So, the example they gave is cutting something in half, and then in half again, and in half again, and in half again. And would you finally get to some piece that's so small, if you cut it in half again after that, it just wouldn't be whatever it was. And that was the word the ancient Greeks used was atomos, and it meant that it could not be divided. Dalton is the next scientist. He comes along in the early 1800s, and we've studied his atomic theory. Elements are composed of tiny atoms. Atoms cannot be divided or destroyed. Atoms of the same element are exactly alike. Atoms of different elements are different. The atoms of two or more elements can join together to form compounds. He was also thinking that the atom was a hard marble, which we no longer think today. And then the next model is Thomson's model. Thomson's model He had this gooey charged substance here, okay, 1897, okay? And he shows the electrons in this positively charged loop. He called the electrons corpuscles. Okay, and Rutherford, you know, things are moving along here. We went from 430 BC to, 1800s, and then, only 11 years later, Rutherford is coming up with the idea that there is a nucleus and the electrons are around the nucleus. And just a few years later, 5 years later, Bohr comes up with the ideas that they're actually traveling in different energy levels around the nucleus, like planets around the sun. And then the modern electron cloud model just shows all the positions around the nucleus where the electron could be. So we know that they're traveling in those energy levels, and there's a specific number of electrons on each energy level. But they're not flat, just going like an orbit. They're whirling all around. Yeah. Okay. Now, this part is, there's a lot of vocabulary. So we're going to go through some of the basic vocabulary for the unit here. So this is going to be an important page to refer to. Okay. And you got to pay attention to this and work with this vocabulary on the study sheets I give you. One of the problems a lot of students have with this is almost everything is called atomic something. So you just going to have to work with it. The atomic number is equal to the number of protons in an atom. So it's a large number at the top of the box for each element on the periodic table. And it identifies the element. So if we say it has an atomic number of 6, it means it has 6 protons in it. And that would also identify the element. The only difference between each element on the periodic table and the one next to it is the number of protons. So for example, hydrogen has 1 proton, and its atomic number is 1. Helium has 2 protons, and its atomic number is 2. So every time that there's a new proton in an atom, it's a different element. So all the elements on the periodic table are made out of the same kind of protons and the same kind of electrons. So if we were going to recreate everything in the universe, all we would need is a jar of protons, neutrons, and electrons. And they could be all the same. And if we made an atom with just 1 proton and a neutron, it would be a hydrogen. And if we made one with 2, it would be a helium, and so on. And we can recreate all the elements on the periodic table from those 3 ingredients. The atomic mass, which is at the bottom of the box on the periodic table, equals the number of protons plus the number of neutrons. When we look at a box on the periodic table, it doesn't ever tell us directly how many neutrons are in an atom. But we know the mass is protons plus neutrons. So we know this total. We know the number of protons because that's the atomic number. So we can figure out how many neutrons there are by subtracting the total of the protons plus neutrons. If we take away the number of protons, which is the atomic number, what's left are neutrons. So the number of neutrons equals the atomic mass minus the atomic number. An isotope is the same element, but it has a different number of neutrons. So sometimes, like carbon-12, carbon-13, and carbon-14, they're all carbon, they all have 6 protons, but some of them have 7 neutrons, and some of them have 8, and carbon-12 has 6. So they're all carbon, but they have a slightly different mass because of the extra neutrons. And in here, example, carbon-12 and carbon-14. Carbon-14 is a special kind of carbon that's found in all living things, and it deteriorates over time into carbon-12. And so when we talk about carbon dating, that's what they actually use, is the carbon-14 left in something. The number of electrons is always equal to the number of protons. So the negative charges always equals positive charges, which means the atom is neutral because the positive protons cancel out the charges of the negative electrons. So 1 plus and 1 minus make a 0, so it's neutral. And since they're always equal in number, all the pluses and all the minuses cancel out, and you end up with 0 charge. The unit for mass for the atom, so I put in here the positives equal to negatives. The unit of mass for the atom is so small that it has a special unit, and it's called the atomic mass unit. So the unit for atomic mass is the atomic mass unit. Okay. The AMU is equal to the mass of 1 proton or 1 neutron. So the protons and neutrons in the nucleus of the atom weigh the same or have the same mass each. So there's no difference. And that's why we can just add them together here and have the mass equals the number of protons plus neutrons, and then subtract and find the number of neutrons because they have the same mass. We already touched a little on isotopes. Isotopes are atoms of the same element with a different number of neutrons. Different isotopes have different properties. Okay. The average atomic mass is the average mass of all the isotopes found in nature. So you see this bottom box on the periodic table, it says 12.011. That's because it's the average of all the carbon-12 in the world, plus all the carbon-13 in the world, plus all the carbon-14. So we can see most of the carbon must be carbon-12 because the average is really close to 12. But then there's the 0.11. Those are from the few 13s and few 14s that are out there that raise the average just a little above 12. Okay? And that's why there's always decimals in the masses on the periodic table. Okay? I want you to identify these things, and at the beginning of the next lesson, we're going to go over the answers to these. So we'll see you next time.